Swayam Prabha. Digital India. Educated India.
Okay, very good. Suraj, are you there? He's just showing the answer. Okay, just go up, go up, go up. Suraj, don't go down, go up. Okay, so 10:58. Just wait for 2 minutes. So we're looking at the Gauss-Newton algorithm. So the Gauss-Newton algorithm is a very powerful technique. This is one of the most. Suppose you say that your BTech dual degree, you want to learn some 10 or 15 most important things. Your BTech here, probably you learn the laws of thermodynamics, whatever. And of course, everybody will talk about data science. I believe that if you are going to go in the path of data simulation, optimization, Gauss-Newton algorithm is a very powerful technique which everybody should learn. Okay, so because the funda is that the dou of the variable which you are measuring divided by to the dou of the parameter, and all the parameters in the parameter space, regardless of whether there is a closed form function for that, regardless of whether it can be differentiated, whatever, we can numerically differentiate it. Even if the forward model is very difficult, you can develop a surrogate model using neural network. So this gives a framework of how you, even if you're stuck somewhere, how do you start from the initial condition and proceed? So at the philosophy with the Gauss-Newton is a very, very powerful algorithm which can be used to solve a variety of problems. Then we can do mix and match. We can combine a genetic algorithm or simulated annealing with this. We can start with the genetic algorithm and then switch to Gauss-Newton algorithm. Then you can use the Gauss-Newton algorithm in combination with Monte Carlo simulation. You can do mix and match. You can do a lot of things, and you can solve problems in all fields of science and engineering, or maybe including medicine. Okay, so it's better to get a grip on this. So this is one of the most important things which you learn in this course. Forget about all the other things. How many Maruti service centers are there in India, whatever. Forget about your quiz 1, quiz 2, whatever. Gauss-Newton algorithm, you remember. Okay, so Z transpose T Z operating on delta A is Z transpose T operating on D. So this is the driving vector. This is the vector which drives you mad. So the driver is very important. Okay, the driver is basically the motivation, the desire. Okay, so in fact, if you go deep into the scriptures and philosophy, yeah, I'm doing work. I mean, what is important? What makes you do work? That's what even Adi Shankara asked that question. Why is there first a desire to do work? I mean, so that's why. So this getting to the root of the problem is very, very important. So the driver for this, okay, you may think that the driver for this is the D, which I agree. The driver for this algorithm, of course, the D, the difference between the current iterate and the data. But of course, the sensitivity Jacobian is there. The sensitivity is all 0, nothing can be done. Okay, so Z transpose T is Z. Okay, operating on delta is Z transpose T operating on D. So now all these extras are all the variants of the powerful GNA. So the original GNA, what we have done is basically we gave a simple problem where there is a first order system, where there is a heating also as a heat generation. So all this delta A business is basically for our problem. What is our problem? Theta equal to A into 1 minus e to the power minus dt. For this problem, all this Jamela we did. Okay, so we gave some 6 temperatures. Okay, so please look at it. So Suraj is showing, pin your screen to Suraj's screen. Serial number, time, experimental temperature. So 3.1, 11.8, 21.1, 28.8, 37.4, and 42.5 at respective times of 10, 41, 79, 139, 202, 298 seconds. So there is some. No, all this is basically an excuse. Basically, you want to learn the technique. There is something, some system is there. There is some temperature. There is some time. We want to understand what caused it. Okay, what causes it is there is a model. What is a model? The model is here. What are the parameters in the model? There are 2 parameters, A and B. What are the variables in the problem? There are 2 variables. One is the time, which is independent variable. One is the dependent variable, which is the temperature. So please know the difference between the variable and the parameter. The variable is continuously changing in the problem. The parameter is fixed in the problem. However, it is possible to have different parameters and repeatedly solve the problem. That is called a parametric study. within the problem, within the set of experiments, the parameter is not expected to change. Otherwise, it's a variable parameter. That itself, then you have to do another non-linear or non-linear. Okay, let's not get into that. So please understand the difference between parameter and variable. So we are looking at the parameter estimation. The parameter estimation is posed as an optimization problem where you solve the minimization. The minimization, unfortunately, cannot reduce to a least square form. Therefore, we propose that the minimization is reduced to a least square form for the change in the iterate from the current iterate of A and B. So you start from A and B, and your least square regression is used to obtain delta A and delta B. That's where the logic is all about. So if you want to find out the best values of delta A and delta B, not globally with respect to the current iteration, you have to work out the Z. Z, therefore, will not be just sigma xy, sigma xi, ya, sigma blah blah blah, all that. The Z is basically a matrix of partial derivatives of the dependent variable with respect to the parameters. That is called the Z. That's called the sensitivity of the Jacobian matrix. So if you do that, so the theta fit for some initial values was like that. 0th iteration, you got a very high error of 1054.071. Come down, Suraj. We did the first iteration in the class. I demonstrated on the board. So from 1054, the sum of the squares of the residuals reduced to 92.44, which is very good. But even 92.45 divided by 6 values, it's about 16. Root of 16 is about 4, which means even at the end of the first iteration, if you get the values of A and B and substitute the value of time, your temperature could be off by 4 degrees centigrade. If you're okay with that 4 degrees centigrade, stay with that. But thermocouple has an error of only half a degree centigrade. So you have to go down further. Go to the second iteration. The second iteration, we are getting theta fit is 2.9, 11, 19, 28, 34, and 40. Please look at the column 1. Go to the column 1, Suraj. Column 3. Okay. No, you can't show it. Okay, come down. So you put it in a particular way. I cannot. Okay. So the error you can see. No. Just stay. Go to the last column in green color. So the errors have come down. So compare the red with the green. So the red is basically the previous iterate. The first iterate you get 92.455, and the second iteration is 17.4, which is very good. There's a sharp reduction. Please go up, Suraj. So please note that 1054, that is the error. 1054.071 come down. In one iteration, it became 92. In the second iteration, it became 17. Very good. Now, Suraj, show your MATLAB code. Huh? Where is it? It's here?
Yes, sir.
Yeah, show it. And you can speak if you want. You have the mic, right?
Yes, sir.
Yeah, just speak for 2-3 minutes. I'll keep quiet. Just speak.
Yeah, here next is a time at 10:41:79, like this one already discussed. And byte is a experimental temperature 3.1, 11.8, like this one. And here V is the initial gas of A and B, and this is a by fit function, and this is derivative of by fit, and Z is a derivative with respect to B, and D is forcing vector, and this is algorithm I have written, and I run for 20 iteration. For GA I have written 1.
Yeah. This is the M file, huh? That is the M file. What is that you're showing, Suraj?
Yes, this is result using GA.
Result of temperature? No.
Yes, sir, temperature, sir, theta. A.
Proceeding with iterations.
Yes, sir, proceeding iteration, sir.
Okay, just can you make it a little bit bigger? Is it okay? Screen size is okay for all of you? Jonah Olive, who is that? Student in Narcos?
Yes, sir.
Jonah,
Sir.
you are MTech or BTech?
BTech, sir.
All right, okay. You wrote the quizzes because,
Yes, sir. I have written.
okay, you are in dual degree or
BTech, sir.
graduating
Sir.
this year?
No, sir. I'm in third year.
ME 18B.
Yes, sir.
You are not in my heat transfer class now.
Yes, sir. I'm in other batch, sir.
Because I generally try to know all my students. Jonah, you just tell us that the size is okay for you or we should make it bigger than Suraj?
Yes, sir. It is fine, sir.
Oh, it is fine. So I am old. So I cannot see. You're all young people. Suraj,
Yes, sir.
they are comfortable. So now, how many iterations, Suraj?
20 iterations, sir.
Okay. Now I'm asking you to do live. It's okay? You won't get pressured, right? I'm asking you to do something live now.
Okay.
Show how A varies with iteration in a plot.
Okay, sir.
Do it. Please do it and show it to the student. Hey, this MATLAB code, you gave it to the students?
Yes, sir. Already given.
Okay. Students, see, please make use of MATLAB. We have a campus-wide free net license for all of you. Even if you don't know the code, just run the code. Run this code and try to this thing, and you can easily learn MATLAB. Okay, so in a week or so, you can learn MATLAB. Okay, even though exams are not based on MATLAB, this is an opportunity for you. Okay, try to solve some problem. Whatever problems you're solving in the class, solve on MATLAB. Okay, so that will improve your, it will boost your confidence. So
Plot, sir, A versus iteration, sir.
I cannot see. Can students see that plot? I'm seeing only your code, Suraj.
Oh, okay, sir. I'm sharing, sir.
You show the plot. Plot, you put plot. Very good, very good. There you are. Now you can see that within the fourth iteration itself, it has converged to 48 point something. So what is the solution, Suraj? A is
48, sir.
48. What is the problem number, this one?
Problem number.
What is the problem? Students, you please tell us.
10.
10. So A is 48 and B is? I'm writing something. I'm doing parallel processing. Don't look at what I'm doing. It's a non-negative. There are several processes which are working simultaneously. Okay, so look at what I'm writing here. B is what? Suraj, what is B? Right. Plot B. Plot B.
Okay.
Are you doing, Suraj?
Yes, sir. I'm doing, sir.
How many people are there in the class? 70. Okay. Okay. B is how much? 6.8 10 to the power of -3, is it?
0.007, sir.
Okay. So, as you can see, the Gauss-Newton algorithm is a strong function of initial guess. We took an initial guess like this. Suraj,
Yes, sir.
take a wrong initial guess and prove that the solution will not work. Is it possible or it takes longer time?
Okay, sir. I check.
You check. I don't know. So it's live. It's live. We don't know whether
I change this, sir.
it will change. Come on, go to the code.
Not.
Go to the code, Suraj, and put A equal to 1. Get off the screen and go to the
Yes, sir.
code.
Yes, sir. Yes, sir. I put it, sir. Yes, sir. Not working.
What is not working? No. You remove the code. You remove the plot. You are not able to see what you are doing. You're not understanding.
Yes, sir. Yes, sir. Already, I put, sir, once equal to 1 initial guess, and
Okay.
get results are not converting.
Okay, Suraj. But remove this plot of B and show your code. The screen is showing still B.
Okay.
Okay. Now A is equal to, no, you prove to them that A equal to 1 you have written. Assume that you
Yes,
are
sir.
me. Assume that you are the prof now.
Yes, sir. Yes, sir. Here,
Life is not about, I keep telling you, it's not about whether you can do. I know that you can do, but we have to show. That is the difference between learning and
yes,
teaching.
sir.
Ah,
Here I have written 1 and D
ah,
is equal to 0.004.
Now you run it.
Yes, sir.
Run it.
Yeah, I'm getting this.
You are getting, no, we can't see that. So you just go to the plot and then it will
Okay.
show,
Okay, sir.
because they all know the correct answer.
Yes, sir.
Do it, do it, do it. So it is going to some answer. And in IIT language, it cup, CUPPED, right? In IIT language, it cup. So don't think that it is like Covishield or this thing, or we put it, all the problems will be solved. So this Gauss-Newton algorithm is not a universal cure for all nonlinear problems. So it is strongly dependent on the initial guess. It is also strongly depending on the nature of the Z. Okay. The determinant is such that Z is a singular matrix, but the determinant is 0, it will go for a 6. So it need not be a singular matrix. If the determinant is very small, you're going to get Z transpose T Z inverse of. So once you have, so the determinant is very small, then 1 by that very small quantity will become large quantity. It lead to violent oscillations. If you are taking a wrong initial guess, we proved in the class now today that it will come. Therefore, don't think that once you learn Gauss-Newton algorithm, there's no need to learn anything. So for some problems it works, some problems it works very well, some problems it works reasonably well, some problems it's moderately miserable, some problems it simply doesn't work at all. Therefore, some improvements are required to the Gauss-Newton algorithm. That's what we are planning to do in today's class. Thank you, Suraj. You will come back again. So just remove the screen sharing option.
Okay, sir.
Very good. Thank you. So I put a lot of pressure on him. It's okay. So, each student should withstand. All right. So Akula is back to business. Dear all, please blah 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 attendance. Okay. Now the improvements to the GNA are like that. So the first one was proposed by, they are all proposed by mathematicians and engineers. Marquardt proposed that sometimes because of these violent fluctuations and all that, you have to condition it. You have to condition your Z transpose P Z. So he said that Z transpose T Z plus lambda of I, where I is the identity matrix, operating on del A will be equal to Z transpose T operating on D. This is called the Marquardt algorithm. Please write down. So this is the Marquardt algorithm. It's also called the MA. Please write down, that's a Marquardt algorithm. Okay. Now, Levenberg proposed some improvement over the Marquardt, and then he figured out that there should be some lambda into that I. That I, instead of I, he said that should be the diagonal of the Z transpose T Z. Okay. So he got this idea from Marquardt. He improved this and said that to be lambda of diagonal of Z transpose T Z. And this is called the Levenberg-Marquardt algorithm. It's also called the Levenberg-Marquardt method. It is an extremely powerful algorithm in nonlinear regression. Okay. So this is the algorithm, okay, which works reasonably well for a wide class of problems. Even this too is a function of initial guess. But now if Z transpose T is as very nearly a singular matrix and all that, this will lambda of this thing will take care of. So it can hold on for some time. Okay. Otherwise, you should use other techniques to narrow down the search. So probably what you should do is, okay, please take it down. Please take this down. I have to talk more about the lambda, what lambda is. Improvements. Okay. If you have copied these two algorithms, just do a thumbs up. Okay, because nobody else. Many people have. Now, thank you all. So the lambda is called a non-negative damping factor. It's one more animal. Okay, it's one more animal which enters the problem. So you have to deal with that. Lambda is not something like A and B which has to be retrieved. Lambda is something specified by us. Who? Us means the analyst or the optimizer or the problem or the regressor. Okay, the subject we. So lambda has to be specified by us. You can start with low values of lambda. Please note, if lambda is 0, it becomes a GNA. Understand? If lambda equal to 0, it becomes a GNA. It goes back to your old GNA. And because GNA can cup sometimes, that's why we introduce the lambda. Therefore, if you put very low values of lambda, you are actually trying to approach GNA. But if the problem is highly unstable, you may start with gentle values of lambda. And if the problem is behaving properly, the solution, but it is converging very slowly, you'll slowly increase the value of lambda. So dynamically, you can update the value of lambda with iterations. That you will learn the experience only if you encounter a problem, whether in research or in industry, or you have a startup, you do whatever you want. So in that, you're encountering let's say you're encountering the nonlinear problem. So lambda, you can dynamically adjust. That's what I've written. Lambda is non-negative damping factor. Please start with low values of lambda. If convergence is low, increase it. On the contrary, if lambda is very high and the solution violently oscillates, reduce the lambda. So what is the correct value of lambda? I don't know. That's a wrong question to ask, because the correct value of lambda depends on the iteration. It depends on the problem. How do I know it? Is there a way of knowing it? Sorry. You have to do it the hard way. You have to take a particular problem. You have to start with trial values of lambda, and then you will figure out experience. So you have to learn by yourself. Okay. Choice of lambda is problem specific and comes with experience. Okay. And experience cannot be taught on a blackboard, or we cannot quiz you and grade you or whatever. It comes when you start working on this. All right. Now, is it fine? Okay. Shall we proceed? Any doubts? Can we proceed? Somebody should give clearance through thumbs up. Okay, very good.
Could you keep the right side?
Right side, you didn't write, huh?
Okay.
Who was that?
No problem, sir. No,
okay,
sir.
Okay. Thank you. Okay. The Levenberg-Marquardt. So please take down problem number 11. Okay, so we're going to wait for 15 minutes. So if somebody can give me the Z transpose, the Z and Z transpose, then it will help us. So the Z and Z transpose will come from the previous problem. Okay, from the solution to 10. Can we do that? So, so today's program is, we'll take our time. At least one iteration we'll try to do hand calculation. Then we'll switch over to Mr. Suresh Kumar. He will show the second iteration and subsequent iteration of MATLAB code. He will also show the MATLAB code for Marquardt algorithm. We'll also send this MATLAB code and the solution to you, so that all the students in the class have a good idea of GNA, MA, LMA. Okay. Tomorrow we look at the Jacobian, okay, or the Tikhonov regularization. Tikhonov was the original guy who said that inverse problems are not to be forgotten or not to be attempted, because there is a problem of uniqueness and ill-posedness and all that. So he regularized in a different way. He got some brilliant idea that we will see in tomorrow's class. Now we will do this Z transpose T Z operating on oh no plus no plus lambda of Z transpose T Z. Okay. This operating on a okay, operating on delta I. Yeah. This is Z transpose operating on D. Okay, I think I wrote it right. Okay. What was the value of Z from? So what is the initial guess of A and B? Can somebody tell? Can you come on the mic and tell me? Huh?
35.
35. Who was that? Ananda?
Suhas.
Suhas. Okay. B. Suhas?
0.004.
Okay. Very good. Now, not good. I have done it for many years, but still I get a doubt. Is this Z or Z transpose?
Z.
Okay, Z. It's very good. Okay. Yeah. So please tell the values of Z now. We got those 12 values, right? What are those values from the last class?
0.0392, 0.1512, 0.2709, 0.4265, 0.5542, 0.6963,
Very good. 10. This one.
336.27,
336.
0.276.
Only 336.
Yes, sir.
Okay. Then
1217.944, 2015.849, 2790.07, 3151.443,
last.
3166.688.
Okay, this you should complete. Now, Z transpose T Z. How much is this? We already calculated Z transpose T Z, no? 4 4. So 2 by 2, right?
1.0718.
1 point?
0718. 5885.48. 3.34 into 10 to the power 7.
Suhas, is it? Is it Suhas?
Yes.
3.34. Tell me the third one.
04.
0. Okay. Okay. Z transpose T. Now let us apply the. So do the killer step. So do this now. Put it here. So lambda. What is this?
Sir, it's 10 to the power 7, not -7.
+7. Okay. Hey, Suhas, don't send me into a ditch. It's +7 or -7?
So +7. That's
Okay, 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 all right, okay. So class, please do it now. Lambda, we put it as 0.1 because we don't know how whether it will misbehave and so on. So 0.1 is safe. 0 is surrender. 0 means there is nothing. GNA. See, there is nothing like doing it yourself. I can show it on the computer, this thing, whatever. If you do it yourself, that is the learning. 0.107. Yes. Suraj, is it fine?
Yes, sir.
Okay. Now you add these two. Please add this. Let us get this. Any problem? Who is that? Who is that? Yeah, please tell me this matrix now, 2 by 2 matrix.
one 1.179. 5885.48. 3.6744 into.
Okay, so now see, that is the power of hand calculation. If you just do it routinely on the computer, MATLAB, whatever you say, it's like attending just simply some recorded lecture, whatever. Now, if you see what we have really done is the original GNA, these two elements are changed. Therefore, it is conditioning the Z transpose T Z such that its scope for doing mischief is reduced. Okay, and it is not vastly changed because deliberately we have kept lambda equal to 0.1. If you take lambda 0.6, 0.7, 2, 3, 4, if you take lambda 2, 3, 4, whatever, if it's too high, it will change the character of Z transpose T Z and all that. So you can try, you can do various experiments and it will be great learning for you if you have time. I know you're doing many courses, many assignments, submissions, all that. If you have time, if somebody has time, take that Suraj's code and play with it. Okay, whenever you have time. Okay, if you get some, next week you're going to get a break. Want to do that? At that time it will be fine. So delta A, delta B. Right side is the same, no, Suha? Z transpose T operating on D. How much is this?
33.143.
33.14.
187549.
1875?
49.
That's it. A point and all we leave it. Now solve for delta A, delta. We'll just wait for 5 to 8 minutes. So today, all of you have learned the Levenberg-Marquardt algorithm and calculation, simple 2-parameter problem. You have solved yourself. You have learned it. Okay. Be happy that you can put a badge. I know LMA. I know LMA. What happened? 3 people we lost. Anyway, at least 70 people are coming. That's and yesterday we had presentations for our atmospheric science. Saturday and Sunday I sat, I sat for 6 hours, 4 hours on Saturday and yesterday 2 hours. Quite a corona scare is there. One boy, Amit, I don't know whether he's in this course. He attended the Viva from the hospital. His parents are admitted. Then Palash is there in this course, right? Oh, morning he came. Palash's uncle was admitted in a hospital, so whole night he did not sleep. So yesterday he was first to go. He slept off. Yesterday or Saturday he slept off, and then he joined late. Then we permitted him to present. So okay, as teachers we have to be flexible, no, in between. So there are plenty. So just take care. Kiran just my TA in the other course. All the 4 people in their house. Sister, Kiran, sister, father, mother hospitalized. Father is 60 plus, so he's still in the hospital. Kiran just tested negative after testing positive couple of days back. So he's taken his sister now. Kerala, he's in Kozhikode. So just take care. So this wave, I think, will go on for next 1 more month. I think April end it will come down again. Hopefully by May, June, many people will be vaccinated. It is a very tricky disease. Very painful. I mean, so the whole world is struggling. So what is the point in so much of technology, right? We said we did this, we sent man to the moon. You can do remote sensing, you can do data science, you can solve this problem. You can find a cure for cancer, but even today there is no cure for this COVID. Only vaccine has come. There is no tablet which you can take or an injection which will. We are taking a vaccine for preventing the disease. There is no treatment now. There is no treatment is still supportive. It's like a common cold, right? You still don't have a medicine for common cold. But common cold, we can deal with this. It's common cold. We know it is. We know maximum 7 days. But this is tricky. Yeah. What are delta B?
12.166. Delta.
Suhasa?
13.128, sir.
13.128.
I. 13.1209.
13.12. And B?
3 into 10 to the power minus 3.
But 3, you put some 3 point at least. Huh?
It's a 3.0012.
Oh, okay. Sorry. Into 10 to the power minus
3.
Okay. So that means A is now 48. B is Suraj.
Yes, sir.
What you do is you just open an Excel sheet.
Okay.
Open a blank Excel sheet, which will contain the time and the temperature of experiment. You have that sheet with you?
Blank, sir.
Not blank. Oh, if blank is also okay, just take blank. So we'll do it live. Live dosa. Okay. Take a blank Excel sheet. Okay. Take a blank Excel sheet and do what I'm saying here, what I'm telling you.
Okay.
What I'm going to tell you. Okay. Okay, very good. Nani Seti. Shreyan, 13. Suraj is saying correct. Okay, very good. So I think so you have learnt LMA today. So be happy. It took a long time. See, when I was a BTech student, there was no LMA. I didn't know that. When I was a PhD student also, I didn't know that. I started knowing it after I became a prof. Suraj.
Yes, sir.
10. Write down 10. Come down. 20. Sorry, 41. 41. 79. 139. And then 202. And then 298. 298. Just make it a little bigger, no? View. Zoom 150% or something. There you are. Excellent, Suraj. Go to B column. 3.1. 11.8. 21.1. 29.8. 37.4. 42.5. Okay. Now the C column will be just put a header for the C column is just put zeroth. Just write the word Z. D column heading you put LMA. LMA. Okay. Just come down to C2.
C2.
Okay. 1.372, 1.372, 0.294, 5 point, no, 5 point,
5.294.
Now come down, 9.483. A class, you are able to see what I'm doing? Somebody please say yes or no.
Yes.
Okay, then 14.928. 19.399.
39.
99. So come down. 24.374. 24.374. Now go to D column. Is equal to 48.12 multiplied by 1 minus e to the power of, do that, 1 minus e to the power of minus
3.
no, bracket,
Okay.
open bracket, 1 minus exp open bracket minus 0.007 star A2.
A2. Okay, sir.
Close bracket, right? First for the experiment, close the bracket. Then after the star, you have one more bracket. Exactly. Just return. Just the return key. Copy it, pull it down. Okay. Now demonstrate in the class whether you have improved or this thing or whatever. Just it's all yours, Suraj. Just prove to them that LMA is working. Speak, do and speak.
What will do, sir?
What I will do, you tell me what we have to do. There are many things we can do. Do a parity plot of B versus C and B versus D. Can you do it on the same plot? Forget A.
Okay, sir. So C B versus D.
Yeah. So parity plot is a comparison of. Now you can see that the parity plot is very good. Hey, can you show the GNA on this plot? You don't know.
Yes, sir. I have to write value, sir.
Oh no. Can you show two parity plots on one plot?
Yes, sir.
Then do it. With a different color. This is blue color. Show that an orange color or red color. Oh, okay. This is a jugaad we did now. We didn't plan it in today's class. Suraj doesn't know that. Maybe I'm pressurizing Suraj. He doesn't know that I'll ask him to do all these things live. Suraj, are you doing something?
Yes, sir. Yes, I'm doing, sir.
Okay. Yeah. So class, you can just see that the column B and column D are very close to each other. Okay. So there's hardly more than 1 degree centigrade in any of the temperatures at the 6 time instants, INSTANTS. However, B and C column are sufficiently far away. So therefore, you can see just one iteration of the Levenberg-Marquardt algorithm is so powerful. If you go to the second iteration, you'll just seal it. End of the story. A and B, you'll just get it. So otherwise, you have to struggle for 5, 6, 10 iterations on the GNA. So Suraj is doing something. Suraj, it's okay. We got it. Don't worry.
Yes, sir.
You're doing. What is that 40 point? Oh, GNA also is showing. First. Oh, so he's showing the. Okay. Yeah. So all of you just closely follow what he's doing. So how is playing with Excel? Hmm? Ah, okay.
Yes, sir.
So so compared to the GNA, it is so the error is substantially reduced, right? GNA
Yes,
also seems to be all right. Okay, but now, okay, so this is how we proceed. Okay, so you can any problem. I'm not saying that any problem can be solved with GNA. LMA. Don't say that our inverse prof told like this. And what I'm saying is a general framework. Use it to your advantage. Now, Suraj, go back to the Excel sheet or the PDF sheet of LMA and MA.
okay.
Okay. So this is how you. It is ideal for programming. It is ideal for doing a program, writing a code in Python or MATLAB. You can play with GNA using the Excel, whatever you want. Okay. Now, this is what Suraj, nice work of Suraj. Okay. So lambda diagonal of this thing he wrote already. We wrote this. Okay. And then what is that? The first is the So the first iteration. So we got. You're doing too many things. Okay. 48 point. Yeah. So show the right side the values. 48 point. Go to the right side. Arey, you're jumping too much. At the end of the first iteration, what is the answer?
Yes, sir.
48 and 0.007. Look at what Suraj has done based on his calculations, and we have got the same thing. This is indicated in green color. If you go to the next iteration, he's got 48.55 and 0.00703. Now go to the left side, Suraj, and show the residuals. Okay, just stay there. Just stay there. Okay, the first column is at time. The second column is the temperature, experiment theta data. Third is a theta of its 0th iteration, and the error is 1054 with the initial guess of 35 and 0.004. Okay, now come to the first iteration. It has reduced to 1.5. See, drastic 1000 times reduction in the sum of the residual. Second iteration, it has reduced to 0.905. Now, if you go to the Marquardt algorithm, Suraj.
Okay.
Suraj, I have a request. Tomorrow, you have to show this, program it for the Tikhonov regularization.
Okay.
And then also write a MATLAB code for subsequent iterations. And then we'll cross compare Tikhonov, GNA, Tikhonov, MA, LMA. Is that okay?
Okay, sir.
And then the proof of the Tikhonov at the end of tomorrow's class, that PDF, you can send it to them. I don't want to spend time on the proof.
Okay, sir.
Understood? Okay. Now show the, okay. So this is the Marquardt algorithm. Show the working of the Marquardt algorithm. Right side, you have the lambda of I, blah, 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 all that. Okay. So this is the Z transpose T. Stay there. So Z transpose T Z plus lambda of I. Okay. Lambda of I is just, he's adding, wait, Suraj. Left side, go to the left side. Just wait, just stay there. So look at this Z transpose T Z and Z transpose T Z plus lambda I. So Z transpose T Z 1.017. So identity matrix is 1001. Multiplying by 0.1 is 0.100.1. So A11 and A22 just 0.1 is added. The funda is, if 0.1 is added to B22, it's like adding some salt to already go to the Marina Beach and add some 1 spoon of salt. It makes no difference. The 33400 is such a high number. Anyway, Z transpose T Z plus lambda I change the 1.07 to 1.175. To that much extent, it should help us. So come to the left hand side, Suraj. Okay, you have to show the answer, right? First show the answer and then the residual.
Yes, sir.
Okay. Now A new seats, so from 35 straight away it went to 48, but the Marquardt went only up to 35.79 and B news 0.009. But in the next iteration, it comes to 45 and 0.007. So it is a little slower, but it also is a conditioning this thing. So if you have wrong guesses, Marquardt may be better than GNA, but it is not as fast as the LMA. Now go to the left side and show the residual. Okay. Yellow 1054, green first iteration 145, yellow again next iteration is 12. It is working, but it is working a little slowly. So you can stop the screen share. Thank you, Suraj. So I'll go back. Okay. Any doubts in today's class? So we did, today's a very important class. So we did variants of GNA. We showed you how to do hand calculation. We demonstrated it on the computer with the MATLAB code. The MATLAB code is given to you. You can play with it. You can solve some other problem. If you're doing your data science program or something, if you have some other program, just try for fun. Try the Levenberg-Marquardt or any other problem. If you have something, some doubts or something, you can ask Suraj and Akula, and I'm already getting a lot of mails. If it is not solved by them and this thing, then it can be escalated and I can help you. Okay. It's Saturday, Sunday, we start for the presentation. Today it's my second class and afternoon I have to do my editor's work. 2 days I have not done it. Okay. Any doubts? Okay. So tomorrow we are going to do the Tikhonov regularization. That is also fun. Okay. On the same problem. So if everything is okay, you can just do a thumbs up so that I can sign off. And
Sir, I
yeah.
have a doubt.
Yeah, who is that?
Shreyan.
Tell me, Steve.
So, in diagonal of Z transpose Z, you didn't multiply A22 by 0.1.
I multiply.
No, you didn't in the calculus.
No. Suraj, you have done it, right?
Multiply, sir.
Yeah, we have multiplied. Maybe I didn't show it. It was done. Huh?
Okay.
We have to do for both. Maybe that was a slip, but you have to do it. Is it okay?
Yeah, okay.
All right. Any other doubt? So if somebody can put a thumbs up, then we can sign off. Very good. Pratiksha, Manthan. Okay. So fine. So just go through this. If you want, go through the video recorded lecture and try do using MATLAB. Try the MATLAB. So we have a campus-wide network, campus-wide license. Okay. Thank you very much. Tomorrow 10 o'clock.